So when you're designing for massive scale, you run into a fundamental engineering challenge, right? How do you handle a complete flood of user traffic without the whole system just falling over? Let's break down the one architectural component that makes this all possible.
And just to be crystal clear on the scale we're talking about, a large data center is expected to handle millions of requests per second. That's the baseline we have to engineer for.
So the real question is, how do you architect a system that doesn't just survive an onslaught like that, but actually thrives? How do you deliver a fast, reliable experience to every single one of those users?
Well, the answer lies in this absolutely critical piece of infrastructure, the load balancer. Its main job is to act as a kind of traffic cop, or a reverse proxy. It takes all those incoming requests and intelligently distributes them across a whole fleet of back-end servers. This is what stops any single server from getting overwhelmed and causing a total system failure. Now, from an architectural view, the position of the load balancer is totally strategic. It sits right behind the firewall. It is the very first thing user traffic hits inside your data center. So its performance, its routing logic, that is absolutely critical for the health of the entire system. So what does a load balancer actually get you? Well, it really provides three core capabilities. First, horizontal scalability. It lets you add or remove servers on the fly. Second, high availability. It does this thing called transparent fault masking. Basically, if a server in the back dies, the load balancer just reroutes traffic around it and the user never even knows anything went wrong. And finally, performance. It's smart enough to send new requests to the healthiest, least busy servers in the pool.
All right, this brings us to our first huge architectural decision. See, it's not enough to just say, let's use a load balancer. You have to decide where in the network stack it's going to operate. We're talking about the OSI model here, and specifically the massive trade-off between Layer 4 and Layer 7.
And this really shows you the fundamental trade-off. On one hand, you have a Layer 4 load balancer. It operates at the transport level, so it's making decisions based on network info like IP addresses and TCP or UDP ports. It is incredibly fast and super efficient. It's perfect for things like session affinity, where you need to make sure all the packets from one connection always hit the same server. But on the other hand, you have a Layer 7 load balancer, and this thing brings application-level intelligence. It can actually look inside the requests, at HTTP headers, URLs, cookies, you name it. This lets you make way more sophisticated routing decisions. This is also where you do advanced stuff like TLS termination, which takes the heavy lifting of encryption off your application servers. It's a classic engineering choice. Do you want raw network speed, or do you need deep application intelligence?
And that choice leads us directly into our next critical design decision, state management. Do we engineer this thing to be stateful, meaning it remembers past user interactions? Or do we go stateless, where every single request is treated like a brand new, independent event? So in a stateful architecture, the load balancer is basically keeping a big table that maps ongoing user sessions to specific backend servers. This is absolutely essential for any application that needs to remember context between requests. Think of an e-commerce shopping cart, right? The trade-off, though, is a big increase in complexity and overhead, because that state might need to be synced across a whole cluster of load balancers, otherwise the load balancer itself becomes a single point of failure.
Now, the alternative is a stateless architecture. In this world, the load balancer has zero memory of past requests. Each packet is routed completely independently, usually with an algorithm like consistent hashing, which can figure out where requests should go without having to store any session state. As you can imagine, this design is way simpler, way faster, and just inherently more scalable. And you know, this quote from the source material gives us the absolute perfect use case. If all you're doing is serving up static files, like images or text, there is zero reason to track sessions. A stateless approach gives you all the performance and scalability you want without any of the complexity you don't. But here's the critical thing to remember. These architectural decisions are coupled. They affect each other. If you choose to go with a stateful approach, you suddenly unlock more sophisticated routing algorithms. For example, the least connections algorithm requires the load balancer to know, statefully, the active connection count for every single backend server. That's how it can be smart enough to route new traffic to the least burdened machine in the whole pool.
Okay, so this brings us to the final piece of the puzzle, automation. A modern, high-availability system just can't rely on a human to respond to failures or to scale capacity. The system has to be designed from the ground up to be self-healing and elastic.
And this self-healing process is actually pretty elegant and super effective. The load balancer is constantly sending out these tiny little heartbeat packets to all the servers in its pool.
If a server fails to respond within a certain time, boom, it's immediately marked as unhealthy and taken out of the active rotation. All the new traffic is then instantly rerouted to the remaining healthy nodes, and it all happens completely transparently to the end user.
And what's really cool is that this exact same automated health checking mechanism is what gives us seamless elasticity. It doesn't matter if you're adding 10 new servers to handle a massive traffic spike or taking them away during a quiet period, the process is identical. The load balancer just detects the new or missing nodes and adjusts the traffic flow accordingly. The user has no idea anything changed.
So, as we wrap this up, this is the question I really want to leave you with. When you're the one on the hook for designing the next highly available, scalable system, what's your priority going to be? Are you going to optimize for the raw, uninspected speed of Layer 4? Or will you leverage the flexibility and the application-aware intelligence that only Layer 7 can give you? The right answer? Well, it depends entirely on the problem you're trying to solve.